Welcome, everybody, to the session on MCD RAM and KNL. My name is Chris Cantalupo. I'm going to be giving a talk today about using the new KNL features and some of the software that enables it. I'll be giving to give you a little introduction about who I am. I'm a software engineer at Intel. I developed the Memkind library along with some other software engineers. And that's one of the ways that you can access the on-package memory in KNL. Prior to that, I'd been working on some benchmarking tools, and my newest day job is working on some distributed power management software for clusters. So if you have any questions about that, I'd certainly like to entertain those too. So, okay, if we can, how do I advance the slides here? Is it? Okay, so this is a preview of a tutorial that Karthik and Rishir and I will be giving tomorrow at SC. So there's quite a bit of information here, and we're going to be kind of skimming over it in this presentation to compact it down into 45 minutes. So I encourage you all to get the full demo and presentation tomorrow at 8:30 in room 18A. I think it's actually changed because of its popularity. It's moved to a bigger room next door. So I think that room number is actually off by one. Yeah, we'll have a lot more information then, and we'll be going through an actual tutorial. We'll show you how to use some of the VTune features and Memkind and do some compiling. And we've got a virtual box for you guys to play with and stuff. So should be a good time for everyone. Also, yeah, there's a little bit of homework. If you do want to join the session, please download our virtual machine that we have posted there on Google Drive. It's an 8 GB download. We'll have zip drives available during the tutorial. We've got 20 of them to go around. So there's other methods, but it'd be nice if you'll had that on their hard drive before they showed up. Okay, so in this talk, there's a bunch of acronyms. We like acronyms at Intel, and I'm just laying those out here. Yeah, when we talk about bandwidth, often we abbreviate that BW, even though it's one word. MCD RAM is multi-channel DRAM, which is the new high bandwidth memory on package for KNL. I'll be referring to that quite a bit. KNL is our second generation Xeon Phi coprocessor and processor that is going to be released in Q1, I believe. NUMA is a non-uniform memory access. It's a Linux and other. It's a hardware feature really, but exposed in Linux, and we'll be talking about some of those Linux features. DDR is sort of standard memory, what you're used to sitting in your DIMMs, and that's sort of backup on KNL systems. And Haswell is, Xeon processor line is fairly recent, and it has some of the, it's required for doing some of the pre-work. That is to say, if you want to test some of the hardware features that will be available in KNL, you can do it on Haswell. Not the on-package memory, but some of the other counters that we use. Okay, so in this tutorial we'll be giving tomorrow, we'll be going through all this in detail, as I said, but our main objectives here are to explain to everybody, what is MCD RAM and KNL, how do we use it, what are the different modes that you can boot this thing into. And then the next step is to figure out, if this new technology is useful for your application. And so we'll talk about how you might be able to figure that out using some of the Intel tools. And finally, once you've discovered that this technology is useful for you, how do you actually put that into work? And we'll talk about the various ways of putting structures into MCD RAM. Yeah, we're not going to really do the functional testing here in this demo, but we'll do that tomorrow. Okay, so what is MCD RAM? MCD RAM is this on-package memory for KNL, and we'll go through an image of the die soon. You'll see how it's laid out. But we've placed this stacked DRAM into the package, and it's quite fast. It's about 5 times more bandwidth than DDR on the same system. The latency difference is fairly similar, and we'll talk about some of those latency issues in a bit. Yeah, so we'll talk about finding your data structures using VTune, how to allocate them, and how to test. So here's an overview of the die for KNL. As you can see, there's a grid of tiles. There's 36 tiles. Those are the CPUs. Outside of those tiles, you can see the on-package memory there in MCD RAM boxes on the top and the bottom of the diagram. And on the sides, you can see that there are 6 channels going out to DDR. And so that's the way that the processors are connected to the memory through the on-die mesh interconnect. The cache is maintained, coherency is maintained, and then there are the various channels to get to MCD RAM and to DRAM. Okay. If there are any questions during the talk, please speak up. I'm happy to answer them as we go. Okay, there are 3 different ways that you can, well, if you include hybrid, there's several hybrid modes, but there are 3 different ways that you can boot KNL to use MCD RAM. The first is a cache mode, which is basically transparent to the software. We use the MCD RAM as a cache to DDR through hardware enablement. And as far as the user is concerned, they will not have to do any changes to their program. They'll have higher latency when they do have misses that go all the way to DDR because they'll have 2 hops to get to DDR. Yeah, and that.
Is the latency of the MCD RAM faster than the latency of DRAM?
They're fairly similar.
Could you repeat the question?
Oh, I'm sorry. I'll repeat the question. So the question was, what is the difference in the latency between DRAM and MCD RAM? And my answer to that question is that they're very similar when they're accessed directly. The effect that I'm talking about here is the fact that when you have a miss to DDR, when you're using MCD RAM as a cache, you have to go through the MCD RAM, so you get an additional latency when you're using it in this cache mode. But if you're using it directly, the latencies are fairly similar. Okay. In flat mode, the MCD RAM is exposed as a separate NUMA node, and so it has the same characteristics as a NUMA node in a Linux system insofar as you can measure the distance to it, and you can use mbind to bind your memory to it. The thing that's a little peculiar is that the distance that's given to MCD RAM is significantly higher than to DRAM, and the purpose of this is to keep standard allocations from landing in MCD RAM and make sure that the application that is using MCD RAM is using it by purpose. In particular, you can keep the kernel out of MCD RAM in that way.
When MCD RAM in the cache mode, can you actually bypass cache, like with multi-portal partners, stuff like that, or data will always land?
No, it's a hardware-enabled feature, so there's really no way to bypass it by software. Mm-hmm. Okay, so right, as I was saying, that when you're using it in flat mode, it's just a separate NUMA node, but the NUMA distances are made quite large so that standard allocations don't land there. In fact, until you run out of all of your DDR, no standard allocations will end up in MCD RAM in flat mode. And for that reason, you have to make special efforts to get your memory structures into MCD RAM, and we'll talk about some of those techniques. There's also the possibility of this hybrid mode, and there you can divide your MCD RAM into part of it used as a cache and part of it used mapped in flat mode, and so you get some of the benefits of both and some of the downsides too in terms of the latency issues. Yeah, so I actually kind of reviewed a lot of the information on the slide in going over that, but just to be clear, if I've missed anything, one of the things I didn't discuss is about addressable memory. So when you map it into flat mode, of course, you end up with more addressable memory because using it as a cache, you can't use it separately. So the benefit of, one of the benefits of using flat mode is you get 16 gigabytes of extra memory, which may or may not be significant depending on how much DRAM you have in your system. Yep, and as I was mentioning before, there are some, if you're using it in flat mode, you do have to make some efforts in software to get your data into MCD RAM, and there's also the additional complexity of having to track a limited resource that the MCD RAM is. You only have 16 gigabytes of it, you got 240 threads, you have to be careful about what goes in and what goes out. Mm-hmm.
Can you turn it off?
What do you mean by?
Can you not use the MCD RAM and just turn it off, or is it always on?
Well, I mean,
there may be a question is why you want to, right? But can you?
I mean, if you're talking about power concerns, I think the answer is no. I could be wrong about that. But in terms of using it in flat mode, it's effectively off because you have to explicitly use it, right? So you're not going to be doing any memory access in that mode unless you explicitly request it. Yep.
What about debugging? Does the runtime
Yeah, in terms of your programming environment, it's just another NUMA node in flat mode. In cache mode, it is hidden from software, so you can't really debug past, the same way you can't easily debug the cache. You can try to infer some things about it. But when you're exposing it in flat mode, it's just another NUMA node, and all of your standard debugging tools will work just as they had in the past with other NUMA configurations.
So
Yeah.
do you have any numbers for the using as flat mode for the bandwidth, latency versus DDR?
You're asking for specific numbers about bandwidth and latency issues. I'll see if they're here. I don't want to quote anything off the top of my head because I sometimes get those wrong, but in general, it's about a factor of 5. So going from DDR to MCD RAM, you'll experience about a factor of 5 increase in bandwidth and fairly similar latency. Okay, so now we have some sense of what the hardware is, how it works. Let's talk a little bit about figuring out if it's a useful feature for your application. And I'm going to skip through these slides because there's quite a bit of information here, and I want to make sure that we meet our time deadline. But VTune, Intel VTune amplifier gives you a new feature with the newest release, the VTune Amplifier XE 2016, which, by the way, is available in the Open HPC distro, which Intel's also discussed publicly just recently. You can use the VTune analysis to measure which memory objects are bandwidth intensive, which ones have the highest bandwidth requirements, and try to isolate those through VTune so that you can go back and modify your application accordingly. So we'll talk a little bit about that there. And I don't have the time really to go through all these specifics, and we'll go through them in the demo tomorrow. But you can see that there's some new features. You can basically categorize what you consider to be high bandwidth on your Haswell system. This is all can be done on your Haswell system to get prepared for KNL. And so you can plot these maps of bandwidth over time, and you can see how your application is utilizing memory bandwidth. And you can even then go forward and see, well, on this line of code, this data structure had this much bandwidth access. And it's pretty interesting how much you can drill down into the actual source code and find the data structures. And eventually, just basically use that information to go and modify your software. So we'll be going through that whole process tomorrow, and I invite you to come for that. All right. Yeah, so there's a few limitations with the latest VTune involving how tracing stack and how you can filter down. But it is a pretty useful tool, and I'm sure they're working on improving some of those features. There's some limitations in terms of the actual hardware counters that are available. All these memory accesses are uncore, so there's some tricks that need to be done to trace back to the actual cores that are accessing the data. Okay, and so this next part of the presentation is about how you would actually allocate your data as an MCD RAM, data structures as an MCD RAM. Right, so there are really, when we're in flat mode, you have actually several options for allocating your structures in MCD RAM. One is, and maybe I should back this up a bit, these different modes of operation, these are BIOS settings. So this is something that you set when you boot your computer, and it can't be changed through the runtime. So I didn't mention that earlier, it's an important point. So depending on your installation, if you have a major installation with KNLs, they may choose one setting or another, or they may have subsets of their cluster which are booted in different modes. It's not really clear how different sites will make use of that, but it is a BIOS setting. You can't change it during runtime. You can't change it without rebooting. And so if your system is booted into flat mode, you still have a number of ways of automating the allocations at MCD RAM. The most obvious way is through NUMA control. This is a standard Linux utility. It's been around for some time, which allows you to direct an application to certain NUMA nodes. And in particular, if your entire application's working set can fit in MCD RAM, it's going to be a very useful tool for just running your application completely out of MCD RAM when your system is booted in flat mode. You can also do things like select fallover and fallback so that if you do run out of MCD RAM using NUMA control, you can fall back to DDR at time of exhaustion. So you can't have fine-grained control of which structures end up falling back into DDR. It's really just a matter of the sequence of allocations that will determine that. But you can have some opportunities to run even if you don't fit entirely in MCD RAM. A second option for doing that sort of sharing of DRAM and MCD RAM with NUMA control is through using the interleave mode. And this way, pages are interleaved over the set of NUMA nodes that you select. And so you can spread out the allocations between DDR and MCD RAM in that way as well. Okay. The second option you have is to use libraries for allocations, and the Memkind library, which I was one of the primary developers on, although I've passed it off at this point, is one way to do that. And it gives a number of different APIs, some of which are fairly basic and straightforward. They look very much like the ISOC allocation APIs, HBW malloc in that family. And then with those, you'll just replace your allocation calls with those HBW malloc calls, and your allocations will end up in MCD RAM. That is, your heap allocations. There's also an auto HBW library, which is available when you build from source of the Memkind library. And this enables you to use environment variables to select a range of sizes that, when allocated from the heap, will end up in MCD RAM. For instance, you could give a lower bound of, I don't know, a megabyte and an upper bound of a gigabyte, and any allocation that is made that's between those two ranges will end up being allocated in MCD RAM through interposition on the malloc and calloc and other ISOC allocation APIs. And as a last option, you can make direct system calls to access MCD RAM. It is just another NUMA node, and you can call mmap and mbind. There's some downsides of that. You can only do allocations in that way with page size granularity. The operating system is going to serialize your calls to mmap, and there's no pool management to avoid making those mmap calls repeatedly. So this is the reason why people use heap managers. It's why there's a malloc call in the ISOC standard, and that's why we've developed the libraries for doing heap management. Yes, I'm sure that that is here in these slides somewhere. I've got quite a few slides, so I'll get back to that when it's on the screen. There's one down there, NUMA control -- membind, and then you pass it the MCD RAM nodes. And in fact, there's also a command line utility for enumerating those nodes that's distributed with the Memkind package, so you can basically just put that in backticks after the membind. Yeah. Yes, let me repeat the question. The question is this similar to the affinitization techniques we use for KNC? And yes, it's exactly the same as any Linux system, really. There's no difference. KNC or Haswell or any other NUMA system behaves the same way in terms of affinitization with NUMA control. Yeah, so I mean, that's the advantage of building on that NUMA technology, is that really everything is as you'd expect. It's just another NUMA node. Okay, so and this is talking again about the preferred option. NUMA control -- preferred allows spillover to DDR when you run out of MCD RAM.
Can I just ask on option A there? So by default, it will just use the MCD RAM. But if you get too big, you'll then go to DDR4. Is that right?
That's right. So when you do, that's for the preferred option. So NUMA control -- preferred, and you specify the NUMA nodes. And then until those NUMA nodes are exhausted, they will be used for allocations.
It's almost like the cache mode, right?
And what, I mean, yeah, it's...
You go into the MC RAM first, and then after that you go to the DDR.
Yeah, there are some similarities. That's certainly true. It's a little different, but yeah, it's similar.
So question here. Why can't you always use a third method instead of the second one?
In fact, you can. The reason you would want to use the second one is if you would like your allocations to fail when you don't have MCD RAM. So that may be a preferred option for you. You may want your application to end and let the user know that the allocation has failed to allocate an MCD RAM. And that's why you would want to use the bind option. But if if you're not concerned, you just want your application to run, then the third option is better. Okay. So here in the slide, we're just talking some of the APIs that are available from the Memkind library and how you access them in a few different languages. So everybody knows, I hope, or maybe there aren't, I don't know. Well, anyway, malloc is how you allocate from DDRs. This is ISO-C standard. It's nothing new there. And you can see the HBW malloc call is essentially exactly the same. You just prefix the malloc with HBW underscore. And there's a whole suite of APIs like that that mimic the ISO-C standard. And if you're working in Fortran, you can use the attributes fastmem, that is to say, if you're compiling with the Intel Fortran compiler, then this attribute will be respected, and any allocatable data structure will be allocated in MCD RAM when it has this attribute associated with it. Yeah.
What if you compile for fastmem but you don't have it?
Yeah, so there are a few different things. So if you compile for fastmem and you don't link in the Memkind library, it will silently not use MCD RAM. So that's something to be aware of. If you use that attribute and there's no MCD RAM available, it'll just allocate it to DDR. So I believe that's how that works. It essentially, let me think about this. Yeah. That's exactly what will happen. So it calls through to the HBW POSIX memoline API. That's what's really happening there. And HBW POSIX memoline is by default in preferred mode. And so for that reason, it will fall back to DDR. With all these HBW malloc APIs, there is a policy that you can set once in your application to determine that behavior. So you can use that same mechanism to switch that behavior if you'd like. There is. Through the HBW malloc, there's HBW POSIX memoline, and that mimics the POSIX memoline feature. And there's even an HBW POSIX memoline p size, which has the ability to choose your page size as well. So if you like that feature, that's available for you as well. And Memkind has all this stuff is built on top of the Memkind interfaces. They're just sort of simpler versions of them. But if you really want to get into the details, the Memkind allows for a lot of different modifications to your allocations. And this is talking about some of that hierarchy there. I don't need to go through every single box in here, but the point is that your application ends up calling through to HBW malloc, for instance. It will then call Memkind, which calls to the user space NUMA APIs, that then interact with the NUMA kernel interfaces to actually go and modify how the allocation works in hardware. And all this stuff is built on top of some BIOS tables that allow us to figure out which NUMA nodes are the high bandwidth memory nodes, in particular the PMTT table. This is an overview of the Memkind APIs, at least some of them. And the HBW memoline is there, and you can see the p-size version of that is also listed there. There's two additional HBW APIs that I mentioned earlier. I just want to bring up again here. The HBW get and set policy, those are the ones that allow you to determine what will happen when you don't have MCD RAM available, or if you would like for it to fall back when you run out. So those sort of things can be set through that policy mode. And you can see the Memkind APIs, which are down below. They look a lot like the ISO-C APIs, but they have an additional argument that comes first, which is the kind of memory that you want to allocate from. And there are several static kinds that are built into the library that you can choose from. And you can even extend those kinds to have different features if you'd like. If you want to get access to the Memkind library, it's been integrated into Fedora 21 and above. It's also part of the EPEL release. So if you are using Red Hat Enterprise Linux, you can add the EPEL package to your system and then just yum install Memkind. That'll give you a version that's after 0.2.2, but before our latest release, which is 0.3.0, which is fairly recent. And if you'd like that most recent release, you can download the RPM from the OpenSUSE build that I've listed there. We have it built in that repository for a wide range of operating systems, everything from OpenSUSE to Fedora and things probably of more interest like CentOS and Red Hat Enterprise Linux and SLES 12, et cetera. So you've got a lot of options there for downloading binary and source RPMs. You can also clone the Git repository directly and build from source. So there's all the instructions on how to do that in the contributing file there. And you can even check out the source code and build an RPM from source if you'd like, using the commands listed there.
Is there a reason why you don't distribute it with the file, the internal file?
Well, in fact, the Open HPC distribution does bundle Memkind and the Intel compilers. So if you use the Open HPC distribution, you'll be able to download VTune, Composer, et cetera. And it also forces you to link into EPEL, which is how you'll get in Memkind. So in some way, they are distributed together through that distro. But there have been some, that's new, I guess, is the point, and that previously that wasn't the case. Okay. Right, and so this is going through here about the different policies. You can set it to bind or preferred, and we talked a bit about that already, but you can also allocate from 2 megabyte and 1 gigabyte pages. You have to pre-allocate those through your operating system with the huge TLBFS, but if you're using huge TLBFS, you can access high bandwidth memory with huge pages or gigabyte pages that way.
With the preferred policy, when I get a pointer, do I get a notification where it was allocated, or can I check where by the pointer value if it's there?
Yeah, that's a request that's come in. There isn't actually an easy way to do that at the moment. It's a feature request for Memkind, and we would like to add that feature. It's actually not trivial. So I just want to talk a little briefly here, and I guess, yeah, I've got some time. So this is talking a little bit about SNC4 mode, and this is a way that you can basically chop your KNL into 4 more or less independent CPUs. That's one way to think about it anyway. It's very similar to, say, a 4-socket Haswell. And in this mode, the MCD RAM NUMA node is split up until 4 different NUMA nodes. So it's exposed to the operating system as 4 different NUMA nodes, and their distances are commensurate with the CPU locality. So you can use it in this mode, especially when you have more than 4 MPI ranks. It's very useful in particular. And it can be useful even for just a 1 MPI rank or just a pure OpenMP threading model as well, but it's a little bit more complicated. Okay, this is just going through some of the basic available utilities in Linux for understanding your memory system. And all of this is really just ways of introspecting NUMA on Linux. But through these tools, you can find out about MCD RAM on your system and what's available. So, for instance, NUMAstat-M will print the how much MCD RAM is in use and how much is available. You can even make that request for a specific process to figure out how much that process is using from the MCD RAM. And you can use the sysfs in a few different places to do some introspection about specific NUMA nodes or about your entire memory subsystem. Yeah, there's also this Memkind HBW nodes API, or application rather, that you can run. It's a command line application, and it just enumerates the NUMA node IDs of all the MCD RAM nodes. So that's a little helpful tool. Okay, so there's also this auto HBW, which I mentioned earlier, and that's not distributed with the packages at the moment, but it is available in source. And it's an interesting solution where we interpose on the ISO-C APIs and then use the environment variables to modify allocation calls. And so this is discussed a little bit here in this slide, and we'll go into a lot more detail about that tomorrow. Okay, so this last section here, we're going to talk about if you have a Haswell system or how you might actually do some functional testing before getting KNL hardware to make sure that you're properly using MCD RAM. So the way we do this sort of experiment, on a standard 2-socket Haswell, the sockets communicate with each other through QPI, the QPI bus. And in this way, we can have, we can use NUMA control to bind CPUs to one socket and then have them by default allocate from DDR that's closely connected to the other socket. In this way, we have a slow memory. That's our memory that's across the QPI bus. And our fast memory is going to be the local DDR memory, and we can use Memkind library to allocate our data structures from the local DDR, even though NUMA control is putting all our default allocations in our stack into the other socket's DRAM. So this little trick allows you to do some functional testing of your application on a Haswell system. It's certainly not perfect. The QPI bus is going to impact latency much more than it's going to impact bandwidth. So it's really just more of a toy, but it does allow you to do some interesting functional tests. Okay, so this is just a bit of a summary of what we've gone through, and oh, gee, I've really gone through these slides pretty fast. So let's just do a little summary then. So if DDR bandwidth is sufficient for your app, which is going to be the case for applications that are not bandwidth sensitive, and there are a number of those. If you're running DGEM or something like that, MCDRAM is not going to help you very much. But you can use Intel VTune to verify your bandwidth usage and how sensitive you are to memory bandwidth properties. Then you can use NUMA control to place the entire app in MCD RAM and see, if that gives you the result that you want and you're able to fit your residence set in MCD RAM. That's certainly the easiest solution for making best use of MCD RAM in flat mode. If that doesn't work for you and you find that you're not getting the right data structures allocated in MCD RAM through that method, you can try MCD RAM as a cache and see how your performance works in that mode. This is pretty straightforward. It's just a BIOS change, but you do have to reboot your machine, and you can try it in that way. And finally, if that doesn't work for you, you could try the AutoHBW library, select a range of sizes, and see if that solution works for you. And finally, if you really have to drill down in your app and make some source code changes, then you'll want to use the Memkind APIs. So we really have quite a range of different ways that you can adopt MCD RAM, and all the way from doing nothing to actually modifying your code and using our libraries. Okay, so that gets us to the backup slides. Can I just pause if there are any further questions? We've had some good questions so far, but please.
Stupid question. What if you use Memkind to allocate in MCD RAM, but then for some reason put NUMA control with Membind to DDR4?
Mm-hmm.
Where are you going to allocate, actually?
Yeah, so that's a good question. So NUMA control sets the default policy for the NUMA policy. And when you use Memkind, you're directly calling Membind, and that overrides the default policy. So Memkind will not be impacted by your default policy. That is controlled by the NUMA control.
So my allocation will end up in DDR4? Or
If you make an allocation through the through the Memkind library, it will end up in MCD RAM.
Gotcha. Okay.
Yeah, regardless of the NUMA control policy that you've set. And yeah, so that's and that's exactly what that methodology is exactly what we use to test Haswell, right? You're using NUMA control to push your default allocations to the far node, and then you're using the Memkind allocations to allocate locally. So that's exactly how that test works. Are there any further questions? Yeah, please.
So can I use like a pipeline in the multi-socket configuration? How it's going to work in case of flats?
To my knowledge, I don't think we support multi-socket KNL. So I think that's the quick answer to your question. Yeah, I don't think that we have OEMs that are putting multi-socket KNLs together. Yeah, there's no QPI. That's the real limiting factor. Thank you. Yeah, so without QPI, it's pretty difficult to put together a dual socket system. Yes?
How about MPI-related communication buffers, space used for adaptive memory? How would a user handle that when you have both MCD RAM?
That's an interesting question. So we've actually very recently had a pull request on OpenMPI to use Memkind as their the allocator, the underlying allocator for the MPI alloc routine. And so that MPI alloc routine is used for allocating some of those buffers that are used for transferring. And it's not clear exactly how the developers of MPI will make use of it, but I guess what I'm getting to is that they are making an effort to do so.
I was kind of thinking lower, like the Omnipod driver memory usage.
Oh, I see. I don't know what the plans are there. So that's a driver that would all be in kernel space, and so yeah, I'm not entirely clear. But with yeah, let me just say I don't know the answer to that, rather than speaking about what I don't know. Yes. No, no, you didn't hear correctly. The question was about when you're in cache mode, and the question was, are the cache misses 5 times slower? No, it's more like a factor of 2 in terms of the latency. So you have a pretty similar latency to MCD RAM as you do to DDR, and so when you miss from MCD RAM, you have to go to DDR. You'll have the latency to MCD RAM, and then the latency to DDR to deal with. So it's just about a factor of 2 in terms of your latency in cache mode. I don't know the answer to that question. I can't speak to the policy of HPC centers, but I do think that there's a lot of benefit to flat mode. It requires a bit of work on the developer side, but I think the HPC community is willing to do that sort of work, and I expect that may be the most successful mode, but I can't predict that. Yes?
Will the prefetchers, the other prefetchers, be aware of MCD RAM?
Okay, I don't know exactly how the prefetchers are integrated with MCD RAM in hardware. I guess I just can't answer that question. But yeah, again, I don't want to speak to something I don't know, so I'm sorry, I don't know the answer to that. Okay, so we have a few backup slides. So you can go to this link here, and you'll see the disclosures that Intel's made about Knight's Landing. You find out all about the details of the hardware there. This is an example of the NUMA distances on a. This must be, yeah. I'm sorry. I think this must be in sub SNC4. Sorry, I was just looking at the title there. Yeah. So this is SNC4 mode. You're looking at the NUMA distances between each node in this matrix. So this is, giving you a little bit of an indication about how the SNC4 clusters are further away than the DDR, but still have a relative distance that is respecting the locality to the CPUs. This is a bit more information about the Memkind interface. I'd certainly be happy to field any questions about this. And since we have the time, I can go through some of the details here. So to begin, the heat management APIs, as I mentioned before, they look very similar to the ISO-C APIs. There is a interesting wrinkle in terms of the free. I just want to bring that up here. So when you call Memkind free, there is the option to specify a kind of memory, but the kind of memory is not required. You can pass in a 0 there, and it will figure it out for you. It's just a matter of optimization. If you'd like it to be faster, you can specify the kind of memory. There's the allocator callback functions, and that's how we actually integrate with JE-malloc, which is the underlying heat manager. And this allows you to specify exactly how mmap is going to be called by the heat manager. Finally, at the bottom there are the kind management APIs, and these allow you to do some introspection and also to create new kinds of memory. And the Memkind is all written in C, but it follows the kernel's lead in terms of doing some object-oriented methods in C. And we use a VTable. It's the head of the structure of the Memkind object, and it determines the operations. So those operations there, they're function pointers. It's a VTable. And that's what you pass in there to create a new kind of memory. So you can override or reuse any of the functions that we have for doing the underlying operations that Memkind uses for doing memory selection. You really have quite a bit of flexibility there in terms of specialization. And that's all I've got for slides. I guess we can go back and look over the VTune stuff. I think that's probably something I skipped through and something that people may be interested in. Yes?
I actually have a question about clustering die.
Mhm.
So if you have, for instance, only one memory bank, one DDR4 memory bank, and you decide to have 4 nodes, right? Just those 4 tiles. Does it mean that only one of them will have access to DDR4 and the rest of them will just only see MCD RAM?
No. I'm not sure I grokked your question, but I'm pretty sure the answer is no.
So, when you have this clustering die, memory controller will be can be accessed by all of those.
That's right. There are 6 DDR memory controllers.
Okay.
So one interesting question you might ask is, if we've got 4 sub-NUMA clusters and we've got 6 channels DDR, how is that done exactly? And it's through some hashing in terms of how we use 6 channels with 4 different nodes, but it works out. Okay, so sure.
Do you know there's like a Memkind provides some allocators for STL libraries in C++?
Yes, that's a good question, and we do, in fact. So there's a HBW how's it called? It's a I'm forgetting the name of it, but we certainly have a standard allocator that's built on the C++03 standard, and you can pass that as the last argument to any STL container, and that everything in that STL container will be allocated out of MCD RAM.
And it's also supposed to take care of the alignment then?
The alignment is a C++11 feature. So the standard allocator for C++11 allows for alignment. The C++03 does not. And what we've implemented for backwards compatibility was a C++03 standard allocator. So you don't have that align as qualifier functioning properly. Now, it's actually easier to write a standard allocator for C++11. There are fewer functions. So that's one of the things that's on our backlog to do, is to have a C++11 standard allocator with alignment properties. Yeah. There's also an example in the Memkind library that shows how you can override new. It's certainly not perfect, but it gives you the ability to inherit from a class. And then once you do that inheritance, at least the members that are local to that class will be allocated from MCD RAM. So it's, if it allocates a substructure, there's another object inside of itself that's not true, that object won't be allocated from MCD RAM. But everything that's local to the object through that example will be allocated from MCD RAM. So you got a couple options in C++ in terms of how you could integrate with Memkind. Yeah, just let me, another point that may be interesting for other developers here is we also are working towards better integration with Fortran so that you can use Memkind with compilers that are not the Intel compiler and have a little bit more flexibility in terms of how that works. So that's something that's coming up in terms of language adoption as well.
Can you go back to the slide where you add all the types?
I'm sorry, I didn't catch that.
Go back to the slide where all the types are drawn.
Yes, one moment. This one?
So which tiles are considered close to which MCD RAM in the sub-NUMA cluster node? But you have 7 lines, so there is one line in the middle which is as close as the top and the bottom.
Yeah. There are 36 tiles, and so there should be 9 in each. It does something that looks a little funny about that diagram, I'll be honest. Yeah, I'm not sure how to answer that question. I think there's an error in that diagram is the way to look at that. I could be wrong. I didn't create this diagram myself. That's right. So I promised a little more detail in VTune. So let's go back to that. So this is.
Is there licensing fee for getting VTune out of the distro?
Yeah, so you can download through OpenHPC all of the Intel toolchain, but you do need a license. So you're free to download all of the software through OpenHPC, but you need to point at a valid license to use it. Now, we do have a number of options, especially for academic institutions, for getting free licenses. So that shouldn't be an impediment for somebody who's doing academic research. But if you are using for commercial projects, you do need a license that is paid for. That's my understanding. I'm not in the licensing business for Intel compilers, but that's I know, and it's also dynamic. I guess that's what I'm trying to get to. We've been changing that policy a little bit, but you do absolutely need a license that's valid in order to use the tool chains out of OpenHPC. Okay. So going back to a little bit more about VTune and how you use it, this is an example here, the ample CL-C usage. And this is how you would actually run your kernel to collect the data. And so this is an example of this GPP kernel, which is something we'll be going over in tomorrow's tutorial in detail. And here you can see from the distribution of objects here that there's quite a few that have low bandwidth usage down there on the left side of the graph, and a number of accesses that are on the higher scale for bandwidth use. And you can slide those bars around to determine what you consider high, medium, and low, and then you can later discover information about those different categories of memory access. Here in this diagram, you can see that it actually tells you the loads and stores and LLC miscount, which is probably the most important metric there in terms of memory bandwidth use. And you can even see that it drills down to particular lines in the code there. So you can see that, I think, in more detail here. This is just a drop-down menu blow-up, and this shows you a lot of your different options for looking at memory usage information. And the one that's particularly useful for you is the bandwidth domain, bandwidth utilization type, memory object allocation source. That guy there will give you probably the best information for doing your analysis. And you can see that we're actually drilling down to the actual line in the source code where the allocation was made. We're saying here that we had a very high LLC miscount on line 128 of GPP kernel F90. You go down there and you look at line 128 and you say, okay, that was where we allocated the W tilde array. So if we go and replace that call with a decorated call to put it in high bandwidth memory, we'll then get the benefit there. And so in this way, you can actually drill down to where you need to modify the code to make best use of flat mode. Here, yeah, we're looking at the various metrics here, but in particular, we wanted to look at LLC misses. That's going to be the most important thing that you want to look into when you're trying to discover the bandwidth utilization.
Sorry.
Yeah.
How's the memory bound metric is calculated?
The memory bound metric?
Yeah.
What's that? Thanks.
Okay.
Yeah.
But look, it's 0.2. What 0.209 means?
Yeah. If we count all the potential execution pipeline slots as one, so then this portion of the one was stored because of like fetching memory from different levels from cache or from DRAM or so.
Okay, thanks.
Yeah. Yeah, I'm sorry, I didn't catch all of that, actually. I'm not a VTune expert, and I know some of the details about how the hardware counters are used, but I don't know all of them. So I don't even know if I could repeat the conversation that just happened. I'm sorry. Could you repeat for me? Or if you'd like to come up? Or?
It was a question how memory bound metrics is calculated. It's calculated from PNU events that allows you to actually, so if, so for example, if we have one as all the potential execution pipeline slots on the processor, then this fraction is like lost because of stalls because of fetching memory from different levels, like cache misses or from different level of caches or DRAM or so. Actually, there is a breakdown, so the column can get like expanded, and then you will see like L1, L2, L3, or LC, and like DRAM, where you are losing the potential execution of byte flows.
Yeah, there's really a wealth of information that VTune gives you, and you can really break down your application into pretty fine grain. I'm really impressed with what they've done with the uncore counters here to figure out how to trace that back to the CPUs that are making use of the memory.
By the way, not all the counters can be correlated with data structures because not all counters has data linear address inside them. So for example, load stores and LC misses, they have address in them, so we can resolve them by data structures. But for example, memory bound metrics cannot be, and therefore you can see the empty cells by memory objects.
Yeah. Yeah. So it's doing well, but there are some restrictions, and that's just based on exactly where the hardware counters are located. You know, they're just when you're measuring bandwidth, memory bandwidth, it's not associated with a particular core. So it's a pretty tricky thing that they're doing there in VTune. It's pretty useful. Okay. Right, and so here we're just talking about how this can all be done on Haswell, and that's a really important thing to note about all this. We can do a lot of pre-work on a Haswell system and get your codes tuned up and ready to go on Haswell, and they should migrate pretty well to KNL. Okay, well, I'm getting near the end of my slot, and we've had a lot of good questions, but is there anything else before closing that I can answer for anyone about Knight's Landing or MCD RAM or the software stack?
36 tiles, is it only decided to 36 no more no less? Number of tiles?
Yes, I understand the question, and I think I'm afraid to answer it, I guess is what I'm getting to. It'll depend on the binning, and they may be different, but I think the 36 is what we're targeting, that there should be extra tiles that would then be turned off to enable binning. And I think 36 is the target number. Okay, well, thanks everybody for the lively conversation and the good feedback about MCD RAM, and invite you all to come up after the talk and ask questions if you have any more that you'd like to discuss. Yeah, and thanks all for coming.